Good evening and welcome to this webinar of the IIT Alumni Center, Bengaluru. A very, very warm welcome and thank you all for being here. When we look around ourselves and we look at all the things that we use on a day-to-day basis, we realize that there is most of that involves mining at some point or other, at some stage or other. And so today we have a series of three talks on mining, in the area of mining, and we are looking at innovations in mining and what the future is going to look like. Especially as we realize that we have depleted the earth and its resources completely, this becomes a very, very pertinent and important subject for discussion at the IIT Alumni Center. So today we have three speakers. We have Professor Rajiv Shekhar, who's the director of IIT Dhanbad, with over 24 years of teaching at IIT Kanpur in industrial applications. He brings in expertise that spreads across multiple disciplines, going all the way from upstream extraction of metals to manufacturing, and also a view of power systems, their optimization, and policy. He's going to be speaking on Mining 4.0 and what is happening at IIT Dhanbad. We will then have Professor R.M. Bhattacharjee, who has been almost throughout at what was formerly the Indian School of Mines, a 100-year-old institution, and now IIT Dhanbad. He spent, after his education at ISM, he spent 13 years in the coal industry, spent some time in the government looking at mine safety, both in India and Australia. And since coming back to IIT Dhanbad, he's now the Dean of International Relations and Alumni Affairs. But one of his specific areas of focus is risk-based safety management. And he's going to be talking about the future of coal and a strategy for action with respect to coal. Again, it's very, very pertinent because here we are talking about renewables and everything else. How does coal fit into this equation? And thereafter, we have Professor VMSR Murthy. He is going to be speaking about the application of mining technology. What else happens with mining technology beyond mines? He is a professor in the Center for Rock Excavation Engineering at IIT Dhanbad. Again, he's been a long time with what was ISM and now IIT Dhanbad. His research interests, including drilling, blasting, excavation, machinery, and underwater structures. Again, he has been working in collaboration with Italy and Australian projects. And one of his areas of interest is the clean mining of coal. He was formerly the head of Department of Mining Engineering at IIT Dhanbad. So thank you all for agreeing to be here and share with us some very, very interesting topics. We have moderating today's discussion, we have Mr. Dipesh Dipu, who is also an alumnus of ISM. He now runs the Genesee Management Consultants, but was formerly with PwC and Deloitte and so on, and is basically an expert in the area of energy, natural resources, and infrastructure. So thank you very much, Dipesh, for having agreed to moderate today's session. A few rules, house rules. We will not be taking any questions that are not typed into the Q&A box. Please do not use the chat window to ask questions. Please put all your questions into the Q&A box. That is what Dipesh is going to be looking at to pick up your questions. The structure is going to be that we have the first presentation followed by a few minutes of Q&A, followed by the next presentation Q&A, and at the end, depending on the time available, we will still have time for questions to any of the speakers. So without any further talk. Let me hand over to Professor Rajiv Shekhar. All yours, Professor. You need to unmute.
Little things. Thank you, Dr. Venkatraman, for your kind introduction, and thank you all the attendees. You know, being the director of the largest non-renewable academic institution is not an easy job, especially because the talk these days is about how the renewable energy systems are expanding their footprint. But let me tell you, ladies and gentlemen, that coal kahin jaane wala nahi hai. It will be present, but in a cleaner form. Okay. Before I start, see, I'm from a metallurgical engineering background, and these colleagues helped me prepare the slides. Professor Dheeraj Kumar, Professor Upadhyay, Professor Pal, Professor Datta, Professor Anupam. Especially grateful to Professor Dheeraj Kumar and all the colleagues from whom I picked whatever little I know about mining. Just to start off, just a few points about renewables versus coal. We all know that the footprint of renewables, especially solar PV, is increasing. It is 38% of the total installed capacity now, and we expect it to increase by 175 gigawatts and by 2022 and 450 gigawatts by 2030. The 2 points that go against the widespread application of solar PV, especially during rainy seasons as we have now in Dhanbad today, or during nights, is the issue of electrical storage. It's very expensive. The other issue is because of the intermittency, what happens to grid stability. But I'm very sure that knowing the ingenuity of the human mind, we are going to get cost-effective solutions for these two problems sooner than later. Another solar technology that is going to come up in the next 10 years is solar thermal technology, which I call as the magnifying glass technology. Similar to coal or nuclear, you concentrate solar energy, but the advantage here is you produce both process heat and electricity. And if you look at 2040, our GDP is expected to double, our energy consumption is expected to double. And believe me, coal will still be a big player. Big with a question mark, but will be a significant player. Now, there are two other issues. You know, once you become a director, you see, you have a holistic view of a system. When you look at a place like Dhanbad or other places in Jharkhand and Bengal, such as Ramgarh, if coal goes, what happens to the people around? Now, would they be turned into a ghost town? And which means that you have to put in a lot of efforts in reskilling. This is something I found out because in IITACB, the number of regular people were employees were low, and we had a number of daily wage workers. Now that we are hiring regular employees, what do we do with these daily wage workers? A simple analogy, but still a very useful one. And you know, whenever we talk about coal, and very rightly so, we talk about the negative impacts, the pollution, the air pollution, the sound pollution, the vibration pollution it creates. But, and the thing about coal is it's instantaneous, you see it. But as far as solar PV is concerned, it's just a matter of time, 15 to 20 years. What are you going to do with the solar PV panel modules that are not used? The big problem there would be leaching of lead and cadmium and other heavy metals, which could lead to pollution of the soil and groundwater. And the moment you do that, as some examples in India have shown, these heavy metals enter the food chain. So it's a question of now or later. So whenever we do a comparison, it has to be a holistic comparison. Now, just to give you some insight in mining, people who are not in Dhanbad or who did not grow up in a coal field, their image of mining comes from movies. If you remember that famous movie Kala Patthar by Yash Chopra and gangs of Wasipur, and you would see miners going down with their cap lamp and the battery pack at the back. Laser pointer. With the battery pack at the back and going down with their picks and shovel to mine coal. That was the image I had too, because I grew up in the coal field, and after I went to IIT and then abroad, I completely lost touch. And when I came back, things had changed significantly. You remember Star Wars? This is R2-D2, the robot, and this is 3PO. And when you're going to talk about mining, this is, and especially underground mining, there would be a lot of automation and autonomous equipments that would be coming in. I'll tell you the reason why. Just to give you a brief example, there are two types of mining. One is an open cast mining, and you can see you dig a giant hole gradually from the top to the bottom. And what you have here is, normally before you hit the coal seam, there is a lot of overburden. And the amount of overburden can be 4 to 20 times greater than the amount of coal you're going to mine. So what you will see here is, you see at the back here, these are sort of mountains. These are basically overburden sitting on top of the coal seams. And these are the equipments here. This is a shovel, and it mines the coal, cuts the coal, puts it in a dumper, and then it is sent to the next processing site. Other equipment that is used, this is a drag line. This boom can be 50 to 100 meters, and it can lift up to 200 to 400 tons of material in one go. This is used to remove the overburden. And then instead of dumpers, in some of the places, you have relocatable conveyor belts that transport coal from the mine site to the processing site. And you're talking about this conveyor, for example, operates at 7,500 tons per hour and 5 meters per second. Now, so the question is, why cyber physical systems? So whenever we are talking of mining 4.0, we are talking of digitization, which to a big extent means implementation of cyber physical systems in open cast mining. So for example, let us see, our expected target is about 1 billion tons, 21-22, our target is, and expected production is about 730 million tons. And the reason we are speeding up, as the Prime Minister has said more than once, that we need to reduce our dependence on imported coal. Now, cost is a big factor here, environment is a big factor. Now, very expensive equipments are used in open cast mining. For example, the shovel which cuts the coal, it can cost up to rupees 150 crores. Dumpers, if you have a 240-ton dumper, may cost up to 30 crores, and the bigger mines, you have 600-ton dumpers. And the drag line I showed may cost up to 300 to 350 crores. So The initial investment is extremely high, and we're talking of more than one shovel, several dumpers, etc. And the availability of these machines is 75 to 80%. If we increase the availability by, let's say, 5%, the productivity would increase by 15%. This is where your CPS comes in. How do we increase the availability of these expensive equipment? Then it comes to environment. When you start off with blasting. You want to create cracks in the seam, in the rock seam and overburden, so that you can mine the rock, overburden and the coal with minimal effort. Okay, and then the mining operation generates a lot of dust. I will show that to you, even sound pollution. Then the overburden dump. The overburden, this is piled, looks like a tall hill. The stability is a big problem. What if it falls while the mine is operating? What if it falls into that giant hole? And then there is this issue of backfilling, because this is not done very rigorously, but the idea is you start off with a certain size of that hole, and as you progress, you backfill some of these holes with the overburden. So these are some important factors, and I will show you how CPS systems are important here. Now, in India, about 95% of the mining is done by open cast mining, for the simple reason it is easier, it is less expensive. But the critical depth is about 300 meters, and we are reaching the critical depth in open cast mines. Then the issue is, and you can see, you make a giant hole, you're going to take up land, the precious land, you're going to take up the forests. So these have implications. So because of that, whether we like it or not, down the line, we have to go in underground mining. By the way, I grew up in a colliery, two collieries. One was Chasnala, there was a big accident, and one was Jeetpur. We are talking about mines that were 1,400 feet deep. Now we are talking of mines with depth greater than 1 kilometer. And at these depths, you have issues such as roof. Whenever you make a gallery for mining, the pressure on the roof caving in, you have methane explosion. When you're looking at this, both from the safety and productivity, automation and autonomous operation are inevitable. And this makes CPS mandatory for underground mining. I'm also going to, there's something in between, which is called Bed Methane, which you have heard of. I'll talk about it later. Just to give you some idea about underground mining, one is longwall mining, and you can see this on the left side of your screen. And if you have a large seam of coal, large chunk of coal, maybe 1 to 3 kilometers long and a few hundred, and let's say 160 to 100 meters deep, then you can just shear it off, along the complete face, and you go along the depth. The other, this is what is called board and pillar. Now, because of the danger of caving, what they had done was, when they mined, they left this coal block. And what it did was, it provided stability to the roof of the underground mine. But the problem here is, about 60 to 70% of the coal is still unmined. Now, getting that is no easy proposition. And this is where, again, CPS issues comes in. And this is a continuous miner here, which is used for example, in board and pillar mining. Now, what I'm going to briefly discuss is the mining chain, mining value chain. I have not talked about it. The first important thing is you have to locate the deposit. Okay. Second is you establish the mine. Third is you operate the mine. Fourth is once you get the coal, you process the mine. And you have heard that Indian coals have a lot of ash. So one of the main purpose of mineral processing is to reduce the ash content. And then obviously the eco-restoration of the mines. So when we are talking about the goals, we are talking about, as you can see, enhanced resource recovery, and then you're talking about the mining aspects and all the sensor networks, etc. And this aspect is very important, resource discovery and location, especially deep concealed deposits, because you have already mined the deposits near the surface, and you have to reduce the risk, simplify the mining operation, make the mining operation smart and sustainable. And what is important is that what we are looking for is mass production technologies and equipment that we develop indigenously, and most of the big equipments are actually imported from companies such as Caterpillar or Sandvik. Green mining initiatives and then promotion of transparency. I'll just skip the slide for want of time. So mineral exploration is a very expensive business. We have 3.11 million square kilometers of mappable area, and only 0.57 million square kilometers have been identified as with obvious geological potential for minerals, and this includes minerals other than coal. So as you can clearly see by the numbers, a major part of this OGP area is yet to be explored. Now, and again, you see the box here, the chances of finding an original deposit is only 0.5%. With odds improving if exploration takes place near a known resource. So essentially, the whole idea is CPS comes in to ensure the accuracy of the location and accurately estimating the quantity of the deposit. Because the main reason is you have to drill holes to get to the minerals to figure out whether they have the right composition, whether they are in the right quantities. And this drilling operation is extremely expensive. So what we are doing here is we have a big geological museum with a variety of minerals. And what we are going to do is we are going to take the hydrological signatures of all the minerals, and then using AI/ML models correlate it with these data sets. These are different techniques for estimating, for measuring and estimating the minerals, gravity, magnetic survey data set. We're going to compare the hyperspectral signature with the data with GSI to help accurately locate OGPs. Now, what about mining? So mining, we are talking of 3S mining, which is safe, smart, and sustainable. And you can see the numbers out there. One is the safety issue, the number of lives lost. The other issue is the amount spent in importing coal. And hence, the challenge here is, and the big thing, as I would show you later, is digitizing in a harsh and dynamic environment and mines is very difficult. Unlike a factory, you have to realize the mine boundaries are continuously moving. So setting up the digitalization process here is much more difficult than what you have in a regular factory. So the challenge here is to design, develop and integrate sensors and communication network, data standardization, and using AI, ML, deep learning with IoTs and blockchain. So this is in general what we need to do in mining. And you can see here, this gives you the figure of the various operations involved. For example, you see this dumper here. So what we have is, we have sensors attached to these dumpers, for example, to measure the quality of if they are hydraulic dumpers, the quality of the oil, how it changes with time. We want to look at the critical elements such as the drive shaft, etc. here. And in a similar manner, the other operations, we will have sensors, and the data will be transmitted to a processing station using IoT, and where the AI ML techniques would be used to at least predict the point at which the machine is likely to fail. And as I said, the cost is important. Recently, one of the drag lines in Reliance was shut out for 2 months, 2-3 months. It was because some electronics had gone bad, and it took them 2 to 3 months to get that electronics, and imagine the amount of productivity that was lost. So if we get timely information about the state of the equipment, that would help increase the availability. And it is not only the state of machines. You have other causes of disasters. So what we are looking at, using CPS to act as an early warning system. For example, you must have heard a large part of Jharia, the old mines, are under fire, which we have not been able to control for I don't know how many years. Okay, so we want to stop that. We have explosion due to methane gas. I lived in one of these, my father worked in one of these collieries in Jeetpur. We had this explosion. Inrush of water in Chasnala disaster occurred because a lake, they did not have proper maps, and they drilled a hole, and on top of that was a lake. It completely inundated the mine. Then you have straight up failure. So all these issues are there. So in short, those were some of the parameters, and because of shortage of time, I will not go into the details, but I'm very happy to state that we have developed this SAGES machine which supports the roof during mining. Otherwise, what we would have, we would be having pillars made of wood or steel, and it has its own CPS system. It will have, hopefully. Now, monitoring a mine is also a very important aspect. For example, many a times we do not know the boundary of a mine. And this could be a source of great dispute. What is the amount of volume that is mined? Because if the royalty has to be paid, it has to be based on the amount of coal that is mined or the amount of mineral that is mined. So smart sensing technologies can be used for this. Pollution. You must have heard about the mining problems in Goa, where the water, for example, was polluted by iron ore, and they would look brownish. And again, with remote sensing technology, by just looking at the color, you would be able to figure out the state of pollution. You would also be able to figure out the state of particulate pollution. So monitoring is a very important aspect. Other aspect, again, which is a source of controversy, is you give mining lease in a certain area and the mining footprint expands without prior approval. How do you find that? And this is where it is important to monitor the mining footprint. Now, one of the problems in mines is, it's easier to communicate with Mars. The signals wirelessly, the signals from Earth can go down to Mars. But 500 meters below the ground in a coal mine, your wireless signals do not work at all. And this is something we are working on right now as a project, because especially with underground mining coming, it is very important to know where each of the miner is at the time of an accident, for example, fire or an explosion, so that we'll be able to locate them and give them a path back to safety. So communication is an important issue in underground mines. This is just an example of an overburdened dump in Jharia coalfields. This is a small size dump. And the stability is a very important aspect here. And we are going to use sensor as technologies to measure the motion of these dumps. And we are talking of a resolution of 1 millimeter or so. So this is something which would be an important part of our work. Now this is what okay, and this is something which is an important part of mining. You see on the left side a dumper that is moving on the road and the dust it generates. This is when a shovel excavates the coal and loads it in the dumper. And this is what happens during blasting. And blasting, it is not only this pollution, this particulate pollution, but there are shock waves also that are propagated. And what they do is they affect, depending on their intensity, they affect the structural integrity of nearby houses. So, I mean, what would be the solution? And CPS use would be wonderful here. So, for example, around this open cast mine, if you have a sensor network which measures the particulate concentration, okay. So once the moment the particulate concentration goes above a certain point, you can release this water spray to cut down the pollution due to transportation of coal in dumpers or during the mining and loading process. And it can also be done during this pollution process, this blasting process. The other important part in blasting is to reduce that. What you have is, let's say this is a, so this is, in blasting, what they do is they make a series of holes. And in the hole, they put in the explosive here and the detonator. And on top, they cover it with soil and they can have water ampules. So once the explosion takes place, these water ampules can reduce this pollution. Now, how would CPS be used here? CPS is important because, you know, how do I know I'm using the optimum quantity of explosives? And I have a grid of these holes. Can I minimize the grid in such a way such that the effect on particulate pollution and shock wave pollution is minimized? The other interesting thing that has been done by our institute is, you know, once you backfill the hole, the question is, I mean, what do you do with that giant hole? At the most, what you can make it, you can have a lake out there, but it would be much better if we can make it habitable, either as offices or homes. So in IIT-ISM, we took a project where we constructed a house, a building on a backfilled zone. Now the problem here is the building is not stable because the backfilled area keeps on consolidating with time, which affects the integrity of these houses. And obviously CPS systems would be great to sort of monitor the stress and movement of the house with time. And then finally, cyber physical system and mineral processing. One is the reduction, right from once the coal comes, then you crush it, grind it, and then you send it to the mineral processing plant to remove remove your ash. CPS would play a big role in reducing the energy, reduction in energy and cost, and better control on size distribution. Size distribution becomes extremely important when it comes to the mineral processing operations. And obviously, then when you're doing the mineral processing operation, you want to automatic setting of reagent dosage. Because one of the problems with the mineral processing operation for cleaning of coal, you have this issue of water wastes. Okay, and these dosages, these reagents are not the most pleasant of reagents to have. Again, as I said, size distribution is very important. So automatic control of your grinding circuit is important. So these are some of the factors that we'll be looking in our technology innovation hub. Now, the next frontier after this, we have coal bed methane, and my colleague here, Rajiv Shekhar, is the expert here. And very simply, coal bed methane is absorbed in the coal seam, and they are formed by the bacterial, microbial action and catalytic activity on the organic matter. Now, what we have here is, so you can see clearly, these are the coal blocks here, and these are the fractures. Obviously, the fractures are not nice and rectangular. So the red dots are your adsorbed methane, and in between in these fractures, you have water. And it is the pressure of the water, and we are talking of about going around 500 meters deep. This is about 500 meters deep, this coal seam. So the pressure of the water holds the adsorbed methane in its place. So the way to get this methane out is you drill a well, there's a pump, and you start extracting water. As the water starts extracting, the methane comes out along with the water, and it is separated at the top. Now, one problem that we are having here near Dhanbad in Raniganj, there is, our expected production is about 40% less than what our production is 40% less than the expected production. And again, the idea here is, do I have the right location for my gas deposit? And there are two factors. One, whether I have the right quantity, and the second, whether I have the right characteristic, because unless you have these fractures, okay, you will not be able to get your coal bed methane out. There are other techniques used as in shale gas, for example, hydraulic fracturing, which is also used. So again, as I said, in terms of location, and then there are a number of wells like these, separated by 100 meters. Obviously, digging these is expensive, and you want to dig them at the right location. What would be if you know the rough location, what should be the spacing between the wells? 50 meters, 100 meters, 150 meters. So what should be the optimum spacing? And then production. So for example, you have 400 wells in one location. Now, some may have some problem because of problems in the pump, or problem in the characteristic of the coal seam here which holds. How do I figure out which wells are not operating to their potential? And this is where CPS would also be very useful. And we have also started in our department, as I said, the final frontiers is seabed mining. We all know 3/4 of the water of our land is covered by ocean, and it's a mecca of mineral deposits. And you must have heard about manganese nodules. So seabed mining and asteroid mining are going to be the next big thing. And mining would be very different from petroleum extraction, where you drill a well and take stuff out. It's going to be much more expansive. So, and then asteroid mining, you have all the issues of logistics, mining in low gravity, etc., safety issues. This has to be these operations in seabed mining and asteroid have to be automated, and they have to be autonomous. So this is something we have started our work on. All the work is being carried out under the auspices of a Texmin, which is a Section 8 company, and it is the Technology Innovation Hub of IIT ISM Dhanbad. So we are doing a lot of exciting work. We also give out projects to private companies, to faculty members, to research institutions who can help us develop cyber physical systems across the entire mining value chain, starting from location of deposit up to eco-restoration. So thank you very much.
Thank you so much, sir, for very elaborate and detailed presentation about the technology here. So I have a couple of questions from the audience, and perhaps because of paucity of time, I will just ask two of them, summarize some of them together so that you can take them together. So the first question is on an issue regarding jobs, basically employment and automation, which oftentimes gets the automation levels of automation oftentimes gets blamed for lack of employment. And given the current circumstances in India, mining sector is often looked at as an industry to create more and more jobs. So one of the questions is that if AI and ML enabled or technology enabled in a larger context, technologies replace human beings, where will people find jobs?
A good question. And I think I alluded to this point earlier. Yes, there would be an issue with people who are lower down on the value chain. And obviously there has to be reskilling. What really makes me excited is, it is very difficult to get students in mining. Even if they go, the good students don't end up in mining, they go to financial consultancy, etc. But with the advent of mining, of automation in mining, I really expect good students to come in mining. It will also open up job opportunities. It will open up when you're talking of cyber physical system. And in fact, what I believe is very soon, companies like CIL will be operating like in the Airtel mode. What does Airtel doesn't own anything? I mean, at least down the line, it will not. It has its business model, customer service, and business development. It will outsource the network, it will outsource the towers. It has already outsourced its billing and all those applications to IBM. So I don't think there will be a decrease in employment. There will be more skilled people required. And some of those people lower down in the value chain, they can be reskilled as, for example, data entry operators, which would be a big thing, and similar jobs. So I'm pretty optimistic.
Sure. Yeah, I fully understand that, sir. And in the past also, when there were lots of concern when computerization, for example, was going on. So of course, the new kind of jobs were created, although there were some jobs lost from the traditional job market. So the next question, sir, is with regard to the technological hub that you talked about and the contribution that IIT Dhanbad is making. I remember seeing one of the clippings where the newspaper talked about how IIT Dhanbad was associated with Mangalyaan mission Mars, so to say. So how do you see this collaboration? What are the specifics of mining in space or those kinds of creating new frontiers, so to say, projects?
A good question. Your guess is as good as mine right now. And this is an area, what we have just started, Professor Murthy is here. Under his leadership, we have first started out, we'll be offering an elective course on seabed mining and asteroid mining. Frankly speaking, our knowledge in this area is very scarce, but I guess in 3-4 years, we would be moving substantially into these. I don't know about asteroid mining, but seabed mining is something we would get into sooner than later. But what are the specifics? We don't have any idea right now.
Okay, great. So the last question, sir, again pertains to cost reduction initiative. And I think you briefly alluded to also that because of harsh conditions, deepening deposits and geotechnical challenges. There is, of course, a cost element attached to all of these difficulties in mining. And one of the questions that was raised was that, diesel prices, for example, have also been rising. So what kind of new technologies that perhaps ISM is trying to develop, which will help the industry overcome the cost issues?
You talked about the diesel prices, you're saying.
Yes, the question was specific to diesel, but otherwise as well, the cost.
We still do not have that expertise right now, but the worldwide trend slowly is moving towards electrical vehicles, even large capacity vehicles. So it is moving towards electrical vehicles. And recently a senior officer in Coal India told me that they have a mandate to retrofit LNG, I think.
Yeah.
LNG in these diesel diesel equipment such as dumpers, etc. So
Yes.
This is another thing that is being looked into. Yes.
Sure. Yeah, I agree. Said one of my clients as well, who was bidding for a commercial coal mine in the recent bids, they were looking at cost efficiency so that they could offer a better price to government for auctioning. So thank you so much, sir, for your time. I would request if you could still be around if there are any more questions.
It's a Saturday. And just I wanted to say, Bajrang Punia has won the bronze and Neeraj is leading in javelin.
Great, thank you so much.
I think he just won the gold in javelin.
Okay, wow. Great. So on that celebratory note, I invite Professor Aram Bhattacharya, who has been a professor, and I have learned quite a lot over the years, not just during the classroom time. So welcome, sir, and address the gathering.
Thank you, Dipesh. Is the slides visible?
Yes, they are. Yes, they are.
Yeah.
Okay. Okay. Thank you, everybody. And now it's my turn. I'm really thankful to Professor Shekhar that being a non-mining person, he has explained so many things of mining. So it has made my job a little bit easier. So I'll not repeat some of the things which I was thinking of telling, but he has already explained very nicely. Now, the topic which I am going to talk is on the future demand of coal in India. What are the challenges before Indian coal industry, and what should be the strategies for action? Now, while selecting this topic or thinking about this topic, I was a little bit confused. What should I speak? Now, the two most critical challenges there in front of the world today, which is having a huge impact on the mankind, I think one of them is the COVID-19, and all of you will agree that this has created a havoc for the last 1.5 years, having a significant impact on the mankind. Of course, I'm not going to talk on COVID-19, but the other issue, which is again another very important and challenging issue, is the global warming and climate change. Now, this is we are all experiencing the effect of this global warming and climate change. Every day we are getting some news that once in 100 years or once in 1,000 years, something is happening in some part of the world in the form of, say, either flood or landslide or storm or something like that. And the entire mankind is struggling now because of this impact of global warming. Now, what is the relationship between this global warming and my talk on future of coal? So we all know that, and that already Professor Shekhar has already explained also, that the coal is one of the, it's thought to be one of the most, the culprit for causing the global warming. So definitely global warming and coal has got some relation. Now I was thinking again, whether the topic should be impact of coal mining on global warming or impact of global warming on coal. So anyway, either of these two, this has got a straight cut relationship, and that is why I thought that I should speak on the subject of future of coal. And if it is future of coal, then definitely what will be the future demand of coal in India in, say, next 20 years or 30 years or so. So that the coal industry can take up and make a blueprint or roadmap for supplying that demanded coal. So, and then again, while if there is a demand of certain quantity of coal, so what are the challenges that is going to come before the coal industry to supply that coal, produce and supply that coal as per the demand, and how we are going to mitigate those challenges. So my talk will be around these four main issues, like that impact of global warming on coal mining or impact of coal mining on global warming. What should be finally the demand scenario of coal, so that the coal industry may prepare themselves for the future. Now, what is the technology of coal production, what we are doing today? What is the best options for production of coal in the near future? And at the same time, what are the different challenges which is going to come before the coal industry and how they are going to mitigate? So these are the four items I'll be talking about. Now, as I told you, that impact of coal mining on global warming and climate change, we all know that for last at least 2 to 3 decades, people are talking on that. And there is increasing concern about the effect of this anthropogenic greenhouse gases on global climate. And the international society, including India, we have agreed to reduce the emissions, GHG emissions. And one of the major contributor of GHG emission is use of coal. Though directly it may not be production of coal, but definitely use of coal. And use of coal mainly either thermal power or industrial use. And in the thermal power plants in India, they're destroying 1 gigaton of carbon dioxide every year. 2.5% of the total global GHG emission is from the thermal power plants. 1/3 of India's GHG emission is coming from the thermal power plants, and around 50% of India's fuel-related CO2 emission is again coming from thermal power. So there is no way we can deny that coal doesn't have any role, or thermal power doesn't have any role in global warming. Now, other than this use of coal, how production of coal is also contributing to this global warming. So one of the major impact is the environmental footprint due to coal mining. We all know that for coal mining, and particularly for open cast coal mining, we require a lot of land. And there is a huge footprint of the mining on the land over the last, say, 50, 60 years. We have done a lot of deforestation because of, we need the land, we need to go beyond the surface. So the forestation, the forest has to be cut. And again, that has got an impact on the carbon capture by the forest, and there has been a carbon footprint there. At the same time, mining produces the air pollution, particulate matters or other different type of gases. And at the same time, water is also heavily polluted because of mining. The third one is fugitive gas emission from mining of coal. It may be a different type of gas, including say methane or CO2 from burning of coal. So all these gases which are being produced indirectly, that is going to the atmosphere and causing greenhouse gas effect. The other very important aspect of environmental footprint due to mining is energy consumption. To produce coal, or to process coal, or to transport coal, everything requires energy. So if our system, if our processes are not energy efficient, we are going to use more and more energy, and indirectly it is also helping in more emission of greenhouse gases and increasing the carbon footprint. So these are some of the areas where we are indirectly causing a concern for the global warming. Now, so obviously we can now understand that definitely coal has got a role, and the entire world now they are arguing against coal. Many people are arguing against coal, and again the government has also taken a lot of policies because we are a part of the international society to reduce the emission. The government policies to create a demand for, because renewables is the main alternative against coal. So we have to make renewables more attractive. So government has created a lot of policies in terms of, say, target of 450 gigawatt of renewables by 2030, the green energy corridor for tapping these energy sources from the solar power from different parts of the country and the distribution to the grid. Then the matter of solar parks for this solar power generation. Then government policies to cut the cost of solar or the renewables, because initially that was the main concern, that the cost of solar power or other powers were so high that it couldn't really compete with the conventional power this source. So government policies are now helping in terms of, say, lower corporate tax or waiver of the interstate transmission system cost charges, or capital subsidy, or 100% foreign direct investment. So these are all these incentives given to the renewable sector for the increasing the demand and producing more and more renewables. And at the same time, because of all these motivational or these incentives, the cost has come down remarkably, and the tariff has now nosedived to around rupees 2.62 per kilowatt hour, almost 20% lower than the power produced from thermal power plants of NTPC. Another very important, negative fact about Indian coal is that our coal is very high ash content coal, almost 30 to 45% ash is there in Indian coal. So our specific consumptions for producing power is very high compared to other countries or other coals. And nowadays, the norms of emission is also very, very stringent. So these are all the factors which is going against the future of coal. Means people are trying to project that demand of coal is going to come down, but at the same time, there are certain arguments in favor of coal also. India is a country of around 135 to 140 billion people, this poor people. And the growth trajectory also, we are hungry about the growth. There are requirement of urbanization, continued industrialization. So these are all driving the energy appetite of this country. And already India is the fourth largest global energy consumer after China, United States, and European Union. However, we are still much behind the other countries like Canada, USA, or Saudi Arabia, or other countries in terms of per capita energy consumption, which is, though it has increased quite a bit, phenomenally, from 16.3 kilowatt hours in 1947 to 1208 kilowatt hours in 2019. But still we are much behind, and maybe not even in the list of top 100. So there is still requirement of the power. So our power demand is going to be growing by around 80%. CE has already projected around 2,500 terawatt hours of gross electricity generation by 2029-30. Other this assessment also is around 2,700. Where presently we are doing around 1,500 terawatt hours. So India will account for nearly 1/4 of the global energy demand growth by during this period of 2040, as per the stated policies scenario. And this is the largest one of any country. And the demand of coal will, though it will be reducing by percentage of in the entire energy basket, but the volume wise, I think it will be still almost, it will be doubled by 2040. Whatever we are producing today, around 730 million ton, it will be around 1,400 by 2040. So the volume of coal production will definitely increase, but maybe the percentage in the energy basket will be reduced. And at the same time, there are a lot of planning for retiring the older plants, more emission and the grid will be improved, and will be having these high efficiency, low emission power plants or advanced ultra super power plants, and that will be improving our quality of this power, more cleaner power. So coal fleet will grow slowly, but definitely will be utilizing it in a much better manner. So as Professor Shekhar already told, that coal is still to stay there. We cannot stop coal mining or use coal for energy for a country like India, but definitely we need to be more responsible in mining of coal. We have to produce coal in a smart manner, in a safe and sustainable manner. And you may get license from the government for your first clearance or for mining, but you have to obtain at the same time the license from the society to operate mines. And that is only possible when we do sensible mining, responsible mining, by taking care of the environment in much better manner than what we have been doing so far. And at the same time, also job creation, employment, social, there's the improvement of the society in and around the mining field through the corporate social responsibility. So there are a lot of things that can be done to make coal mining still more attractive, and at the same time supplying the energy the country requires in future. So based on these two arguments again, I just show you one quick slide that what is the scenario of coal mining in some of the other coal producing countries in the world, like USA, Australia, China, Indonesia, Russia. You can see that I've compared from the 1979 figures to 2019 figures on 40 years, and USA was producing 708 million ton by that time. Their peak was 1,075 only 3-4 years back, and then they have started reducing that, and now it is around 639. Australia started with 106, now they are 503, and the peak was 512. They have slightly reduced, but maybe the demand is there, so the Australian production will be going up. China, phenomenal, 635 to peak of 3,748, just slightly reduced in the last year by 3,692. Indonesia, just unbelievable. They started almost coal mining in 1979 with 0.28 million ton. Now they are 616 million ton, just behind China and India. They're the third largest producer now. Russia, again, Russia's figure is, of course, I'm having that from 1991. So they were 371, now they are 417. So all these countries, they're still producing and maybe slightly reduce their coal production, as because many of those countries are having another alternate fuel source, like in terms of gas and oil, in a much larger reserve they're having, which we do not have. So as India, we cannot really afford to reduce our production of coal at this moment, and we have picked up in from 103 to 775 only last year, 769. But the projection is that we are going to increase by, as I told you, around 1,300 to 1,400 million ton by 2040. And only in 2024 to 23-24, the target is 1,000 million ton, 1 billion ton. So in the energy basket, yes, the thermal coal, now it is total 60.9, renewables, the hydro, etc., 12.1 and 25.2 as of today. But as per the projection, what we can see that coal power will be around 792 by 2030 and 1552 by 2040. And coal will be 269 out of that 792. Of course, you have to mark here that these renewables, it is 137 to 436. We are assuming that this is going to happen by 2030. There are a lot of uncertainties in that field. So if that doesn't happen, then again there will be pressure on the in the coal demand. So the solar power, you can see that it is from 38 to 248. We are really very much optimistic. I am not saying that we should not give the fault, but still we'll have to put our fingers crossed that whether we should really will be able to produce 248 gigawatt from solar power or not by 2030. So if we see the demand now, if we sum up the demand, the lower bound and upper bound, 2,200 to 2,400 terawatt hours by 2030, and then coal-based generation will be around 1,150 to 1,350. For the production of coal, which is required for thermal power, will be around 800 to 875, and coal-based other capacities, coal-based capacity will be 230 gigawatt to 260 gigawatt. And if we calculate that, the figure will come out about, say, 1192 to 1325, though it is a very conservative figure. So even if we assume that we are going to produce this around 1,300 million ton of coal by 2030, or around the same figure or a little bit more than that by 2040, so how we are going to produce that? What are the issues that need consideration? One of them is, do you have enough coal? I'll show you the next slide that how much coal do you have? And then do you have the capacity to produce coal at the globally competitive price and in a sustainable manner with the technology what we are having today? What will be the impact of coal mining and its beneficiation and again global warming if we are going to produce 1,400 million ton by 2040? How to optimize the cost of coal production, not only in terms of rupees per ton of coal, but in terms of cost of environment, in terms of cost of energy, in terms of cost of land, and in terms of cost of GHG emission. So we need to look into as a holistic manner for the overall, what should be the optimum cost to produce the coal, and what are the feasible alternative use of coal that also needs to be considered. So these are some of the issues which need to be considered by the coal industry. As I told you that inventory of coal, which are having almost 344 million ton coal, The proved reserve is around 47, around 155 billion ton of coal. So we still have a lot of coal in our inventory, other than the lignite, which is around 46 billion ton. The production was the last 29-20, it is 730.87, and the growth was around 2 to 7% over the last 10 years or so. Now, if we see the supply side roadmap, what are the challenges ahead? As we all know that we have got basically two methods of mining. One of them is open cast mining, and another is the underground mining. And presuming that we are going to produce that 1300 billion ton of coal with 30 to 35% of the total energy basket, how we are going to prepare our roadmap? What are the challenges before the industry? In terms of production of coal, what should be the mix of technology between open cast and underground? What should be the technology, proper technology for coal production? What will be the environmental impact and how we are going to mitigate them? And what will be the socio-technical and socio-political context which need to be considered? So I'll just give you two scenarios, before nationalization and after nationalization, because that is a very significant era, 1971-73. That time, Indian coal mines, before that it was all private operated mines. In 71, all non-coking coal got nationalized, and in 73, coking coal got nationalized. What are the scenarios before nationalization and after nationalization? Before nationalization, most of the mining was underground mining. It was almost 75-25. That was the percentage of production from underground to open cast. Most of the mines were very small, owned by private owners. They had the lack of mass production capacity. All the mines were below 1,000 ton or maybe 1,000 to 1,500 ton per day capacity. There were a lot of constraints in vertical hoist because all the mines were underground mine with shafts and with binding system, which is obviously a major constraint for higher production. Most of the operations were manual. It was all cyclic mine, drilling, blasting, loading, transport, and lack of adequate safety. A lot of accidents used to take place, a lot of disasters used to take place. Number of fatalities everywhere was very large. So this was the scenario before the nationalization. So then the need came for nationalization because the country wanted more coal, which was not possible by those small owners. So it was nationalized. There was an immediate increase in the coal demand. So the available technology of by underground mining, with mostly manual system, was not possible to produce the required quantity of coal, and the economics of underground mining was also not very poor. So and the potentiality to augment production from underground, again, it is not very large. I mean, you cannot increase the production from 1,000 ton to 10,000 ton in a day. So that is the problem. So all these things led to open cast mining, more and more of open cast mining, because of easy amenable to mass production. You can increase the size of the machine or the capacity of the machines, which is readily available globally and at relatively less cost, and that is why it is also resulting to better economics. So that gradually that gave way to more and more of open cast mine. So the priority shifted from underground to open cast for improving production and productivity. So gradually what happened again, and then another issue was very important nowadays because for open cast, the route of outsourcing. We could very easily pick up the production by outsourcing the activities, the main activities of this overburden removal and sometimes the coal production also. So we have given contracts to a lot of contractors and outsourced the operations, and that has really picked up the production, augmented the production. And at the same time, our capability of underground production gradually start reducing because our focus was lost from underground to open cast. Less priority was given. The target was mainly to produce a total coal, whether by open cast or by underground. So people preferred open cast path. So gradually that has given, and now that is the result that today it is around 94% of open cast and 6% coal from this underground. Just the reverse one, 25-75 before nationalization. But at what cost? Cost of this open cast is definitely less than the underground mining. But there is one cost which has been ignored. That is the cost of environment. And ignoring the statutory and social obligation for so many years before very recent times when the norms become more stringent, the environment was very grossly neglected. And that is why large-scale damage of landscape, poor restoration of post-mining land profile and land use, that has been caused. And the pollutants load has become, gone beyond the carrying capacity of the mining towns in and around the mining field. And late implementation of environmental laws, as I told you, only last few years this has happened, and absence of significant penalty for non-compliance. It was indirectly a motivation for growth of open cast mining. So that has all led to finally that imbalance of open cast and underground production of 95%. I'll give you a very quick snapshot of the production, technology-wise production of CIL, both for underground as well as for open cast. Total underground production in 2020 it was 29.2, whereas the open cast production was 572. And out of that, long-haul technology, which is believed to be the best technology or the mass production technology, it's only producing 1.96 million ton of coal. Roman pillar with continuous manner 6.62, and rest 20 million ton from Borden pillar, SDLN and SDNRS. In the same, in the open cast sector also, shovel dumper combination almost 1100 million ton, dragline only 53.21 million ton. Now in 23-24, the scenario of CIL is just slightly changed, though the total underground coal production will be more by a few million ton, 8 million ton, but out of the total coal production, the percentage-wise it will further slip down, go down. So my question is whether are you going in the right direction or not? I'll also give you another very quick statistics of the size of mines, both in open cast and underground. If you see the size of mines, the total production from less than 0.3 million ton of coal per annum, the mine size and the capacity wise, is 12.98. 136 mines produce 12.98, with an average production per mine is around 0.095 million ton. That is 95,000 ton per year, which is abysmally low percentage of total underground production, whereas it is 82.93 in that zone of less than 0.3. So maximum mines are less than 0.3 million ton per annum, and only a few mines, only 2 mines more than 1, 5 mines between 0.6 to 1. So that is the scenario. In case of open cast also, the scenario is not much different. Less than 3 million ton. 3 million ton is not considered to be a very large production for open cast. 165 mines is producing less than 3 million ton. Only 2 mines more than 30 million ton, 3 mines between 20 to 30 million ton, 12 mines between 10 to 20 million ton. And the contribution also, you can see that 80% coal is coming from less than 3 million ton. So what I finally summarize from this is that we are producing most of the coal from the small capacity, small size mines. So what are the challenges and what are the strategies now? So there is an imbalance of production technology, 95 to 5. More than 80% mines are of very less capacity. And as the mines are of less capacity, there is less scope of automation. We are using large fleet of small machines in all those small mines, and resulting into poor operational efficiency, more cost, poor economics. And as a result, because of lack of this capacity, the infrastructure developed is also poor. And energy intensity of all those mines is very, very poor. And again, I'm putting more emphasis on energy intensity of mining because this is indirectly adding to the cause of GHG emission. And open cast mine is more energy intense because we are not only producing 1 million ton of coal, we are at the same time we are producing 4 to 20 billion cubic meter of waste materials that all requires energy. So energy intensity of open cast mine is much, much higher than that of the underground mine. So there is a need for reversal of the technology mix. What we started in 71, 73, the other direction. Now it is a time for reversing into the other direction. So we should give more thrust on underground gradually. I'm not saying that there will be open cast should be stopped, but at least to economic depth, there will be open cast. Then the closure of small mines, uneconomic mines, it is that harsh decision has to be taken. And there is scope of amalgamation. We have recently made a study of 90 underground mines of whole India, and where we find there are a huge scope of amalgamation of smaller mines to make it a larger mine. And the larger mines have the scope for larger automation, more automation, and use of smart mining system, application of all those cyber physical technologies, AI, ML, all for optimizing machine availability, utilization, operational efficiency. So this requires the capacity of mine or size of mine to be more. As I told you that there is a requirement of looking at the energy consumption. So there must be a regular feature of energy audit in our mines, establishing energy benchmark for unit operation, all the unit operation, and then reducing the energy waste wherever there is a scope by optimizing the fleet size, improving the operational condition, and all this will lead to more efficient, energy efficient mining. The other challenges are availability of land, which is a very big challenge for the mining industry, coal mining industry as on date today, and more so for the open cast mining. I know at least about 20-30 projects as on date today, they are all held up because of lack of land. Land is not available. Land requirement for deeper open cast mine will be much, much higher. So there is a necessity to make a comprehensive study required to assess the land use so far how much land we have used for producing 1 million ton of coal mainly by open cast method. What is the carbon footprint of open cast mining? That is also need to be assessed. And we need to, as I already told, that we need to obtain the social licensing from the society. This lack of social licensing due to poor social perception of open cast mining. Very negative perception is there because of the permanent damage of landscape, difficulty in forest environment clearance. These are some of the challenges before the industry. So what we should we should go for UG mines for deeper deposits. As already mentioned that we are now going more than 300 meter depth, and open cast is not going to be a viable solution for that. Opening of underground mines from the bottom of open cast, that is another feature that needs to be considered. Punch longwall or punch entry mining, underground mining. Then integrated mine planning. Simultaneously open cast come underground. As you go down and down, deeper and deeper, some portion of the mine may be converted into an underground mine, but the planning should be done initially as an integrated mine planning. Underground mine under forest or hilly deposits, that will save the forest. We don't require the forest deforestation under the forest for hilly deposits. At the same time, concurrent backfilling and reclamation to reduce the land requirement. As we are moving on, so it's not at the end of the mining life, the void will be filled up, but it should be done simultaneously, concurrently with progressive mine closure. Effective mine closure has to be implemented, and returning the reclaimed land to the society in a phased manner, not at the end, but during every 5 years, you have to give back some portion of the land which has already been where from you have already taken out the coal. It is reclaimed and it should be given back to the society for, again, maybe agriculture or some other purposes. The land value should be upgraded by even the open cast mining, or the reclamation can add value to the land which might not have been suitable for agriculture initially, but by proper reclamation that can be converted into good land for agriculture purpose. There is a huge scope of repurposing our abandoned mine site. The abandoned mine sites are just left as it is, but it can be used for eco park, facilitating eco-tourism, for water adventure, something like that you can do. We can use those land other than as what Professor Shekhar has given that example of building houses on the open cast reclaimed area. So if you see that what should be the roadmap for the open cast mining in the future, so mining plan, large and mega mines to be planned, and that will minimize the loss of coal in mine barrier. If you have small mines, every mine between 2 mines will be losing a lot of coal, which is we cannot afford. Then optimizing the fleet size for reduction of energy cost, operational cost, and maintenance cost. Now many mines, and particularly those outsourced mines, if you see, we are still using the dumpers of 20 ton to 50 ton capacity, where globally we are using 240 ton or 600 ton, 657 ton capacity dumpers, large size solvers. So there is a requirement of optimizing our fleet size, the process and energy optimization by use of automation and the use of the cyber technology, AI, ML. Each and every piece of unit operation can be mapped through the sensors, and there is a scope of improving the energy efficiency, and energy benchmarking is highly required. Environmental mitigation, we should have comprehensive planning for concurrent reclamation, Effective green barrier is again a very important aspect. We are making plantation in and around that, but how good are those plants as a green barrier against the pollutants? What are the foliage of those plants? What is the density of those plants? That requires to be monitored, and that can be done by use of remote sensing and on these modern methods to improve the carbon capturing through afforestation, reducing the land requirement by compulsory in-pit dumping, monitoring of mine closure through remote sensing or GIS, and specific requirement of environment management, reclamation, restoration, safety obligation in contract management. I'm putting stress on this contract management. Now we are almost 60-40. 60% of the jobs are outsourced. The activities are by contractors. So there must be specific requirement in the terms and conditions of the contract regarding environmental management, reclamation, restoration, and safety obligation. Quality improvement through selective mining, more use of surface miners. These are some of the things that should come in the open cast mining. In case of underground mining, mass production technology. We cannot survive with the small mines with LSD, SDM. We have to get rid of those the semi-mechanized board and pillar mine. We have to go all out for this continuous mining system, underground transport, conveying of coal, material, man. Everything should be this continuous mass production technology like longwall, woman pillar, Wangauli. So these are all available globally. These technologies are available, proven technology. We need to adopt this technology as per our conditions. There are a lot of coal pillars which is standing in many of our underground mines because of lack of proper technology. We can use short wall or use of short long wall method for extraction of those standing pillars in the underground mines. For thick seams, we can think of long wall top coal caving, which is a very, very successful method in China. They're producing many of the mines through this long wall top coal caving, very high quantity of coal. Partial extraction with stowing for build-up areas, because we have got many mining areas or fields which is thickly populated, so there is a requirement of stowing, and that stowing should be matching with your rate of production. So high speed of stowing, that is another requirement, another challenge. Mass inertization as a regular practice. Why it is so important? Because our coal is highly susceptible to spontaneous heating, and many of the mines are already under fire. And you all know about the Jharia fire or fire in Raniganj or other older coal pits. One of the major shortcomings in our system is lack of inertization system. So this is one thing that we need to look into. And then methane drainage for highly gassy mines like Monidi or Sudamdi or this Jitpur, this kind of mine, where prior to mining, methane drainage should be done. Then in case of underground, as we have already understood that indigenation is a very important requirement to support the mining industry, and again, as Make in India program, improved maintenance by using AI/ML or machine learning, machine condition monitoring, more and more of automation, vertical transport system to be improved by incline or large capacity skips or vertical conveyor, continuous and precise monitoring of environmental and strata condition. Safety is one very important issue for our Vision Zero, though our fatality rate is now around 0.18 per 1,000% employed basis, but a lot of frequent disasters have taken place. In last 20 years, 8 disasters killing 167%. So there is a need for changing the philosophy from rule-based safety management system to risk-based safety management system. The commitment, consultation, communication, and competence. These are 4 C's, which is very, very important for changing the philosophy of our safety management system. Disaster prevention strategy should be given top priority. We should have some risk-based emergency management response plan backed by triggered action response plan for emergency management. Learning from experience of past accidents is a very important thing, and that is also only possible by root cause based accident and incident inquiry. So this is one area where we need to give our focus. Automation, teleoperation to reduce the exposure in underground, continuous and reliable monitoring of hazards, and effective engineering controls for the principal hazards. So these are some of the issues for safety. I'll just quickly go to the last slide of my conclusion. We talked about methane drainage and CO2 from the mine fire. So what we should have is coal mining to continue, definitely, though the percentage contribution will be less. but we have to be more responsible in mining with due care to environment, safety, and health. The negative perception of the society to be improved by social acceptance. Land reclamation and repurposing of abundant mines is an important aspect. More thrust on underground mining, increasing share of underground for deeper deposits, large mines, larger machines, automation, application of smart technology, and indigenization at the same time to make in India reliability, self-reliant, and employment generation. And the policy on compulsory coal washing. So these are some of the strategies that should be taken up by the coal industry. Thanks.
Thank you so much, sir. It was very informative, and unfortunately, we can't ask you questions right away. I think it would be better if we go to Professor VMSR Murthy now. And if we are left with some more time thereafter, then we'll come back to you, sir, for more questions. And for the audience, even though we might run out of time, please stay tuned, because the presentation that Professor Murthy is going to make is going to be very, very interesting. So please stay tuned. Thank you so much.
So good evening. So I think after hearing two important views of a synoptic view of mining and its extension to cyber physical systems by Professor Rajiv Shekhar, and a very in-depth coverage of Professor Bhattacharya on coal mining and the roadmap, I think let me take you to the other dimension, that how this mining technology application can be beyond mines. So we'll be covering three major segments here: ports, tunnels, and caverns. As you can see, we'll be focusing on these three areas, and the key focus would be on how this knowledge of mining technology, can be applied in these areas gainfully, so that whatever we talked about, like the other areas of avenues for employment, avenues for research, avenues for academic interaction with industry. So we'll be talking about ports, where widening and deepening is one of the major focus we'll be doing. And tunnels, we'll talk about how do we make them faster, so that we connect people and the places in a more efficient way. And then the rock mass characterization, which is cavern being a third, having a large dimension. So we need to have more in-depth knowledge about rock mass characterization and design. So because their applications are growing daily. So let me just touch upon ports. And in fact, ports are now considered as an eco-friendly mode for trade action. So as you know that the diesel emissions, particularly on land mode, probably would cost us more, as we would like to reduce the greenhouse gas emissions. Probably sea route would be, or inland waterways could be one way where we can achieve this target. So for that you require very nicely developed or modernized ports with deeper drafts, vessels moving in that. So for that requires you require to blast the area, demolish the areas, or deepen the area. So widening and deepening are two important things we need to do. And here comes the mining technology to rescue, because this is the science that we learn in mining, particularly the drilling, blasting has already been touched upon, mechanical cutting, and then diamond buoy cutting also, and several such techniques which you can think of. Though mechanical excavations are sometimes we need to go for, though they are cost intensive, but then drilling, blasting is general choice. You can see Government of India in 2016 has planned for connecting all the ports, major ports, in the process of the port modernization and port connectivity to improve the trade actually. So you can see already we have completed a good number of projects by now, and then we have many projects worth of about 1,50,000 crores of investment is going to be made in and under implementation, and this provides a huge opportunity for business, for employment, and for research. As you can see, IIT-ISM has been striving, considering the importance and the national challenge that has been thrown. It has risen to the occasion, and then we have already started working for the last 15 years, demolition of rock as well as concrete berths for widening and deepening of the ports to pave way for large draft vessels for controlling the trade. So I'll not go into details of this. The scientific challenges probably that come up actually, which we discussed also in mining technology, is ground vibration, because here the blasting is happening at a very close distance, maybe up to 2-3 meters distance. So ultra cautious blasting is what we need to do here. And you can see the ground vibration sensors being placed here, air overpressure, and fly rock, which also is an important challenge. And then you can see the big ships, are there in the ports, which need to be rescued from the impacts of this blast. So these are the challenges that we have taken up, and we have investigated and generated know-how in this area. And as you can see, I think I'll not go into details. In mining technology, the most important thing is how do we fix up our drilling and blasting system. I think these are the important areas that we design, particularly the quantity of explosive. I think these points we have covered, but then how do we redesign the entire system suiting to the situation? You can see the explosive being, divided into several such segments and initiated in small delays, so that maximum charge per delay is controlled and the vibrations are controlled. One of the recent exercise that we have completed, you can see there's a 0.5 kilometer of new berth has been constructed, and the old berth very close to this was to be dismantled. So in a section you can see here, this is the new berth that was constructed to be protected, and this is the old berth, maybe over 50 years old, which had to be blasted. So the two impacts that we need to understand here is the ground vibration causing damage to the structure, new structure, and then the water shock that could cause again a damage to the structure. So these 2 points actually we have investigated, and we have designed the systems, and successfully we have completed. And you can see more specifically doing line drilling and pre-splitting. These are the 2 important technologies that we are doing. So on the left side, you can see the planning that we have done, the charge distribution and all. On the right side, you can see the actual implementation that's happening. This is the berth, that we wanted to protect. And this is the drilling, that's going on very close to the berth. And then we normally do line drilling to separate it, and then subsequently the pre-splitting for blasting it. So, and the other one is like, the anchor walls, which are pretty close of, almost 1.5 meter, 2 meter distance. You can see the kind of vibration that can come up to the new berth actually. So here actually we require to charge design has to be properly done, and the maximum charge has to be controlled. The 2 challenges here are vibration control. The other one is fragmentation. If I am unable to break the rock or break the concrete, then there's no fun in blasting actually here. So therefore, we must ensure that the blasting goes on as desired by the loading system. You can see this is a typical cycle where the drilling goes by a floating bar. You can see that it's a very cumbersome operation. And then you can see a long column of charge being prepared already is lowered into the hole. And then to safeguard the fly rock, we are muffling it with the sandbags and all. And then we, after a careful connection of all the wires, you can see a detonation happen here, and the plume of water coming up without causing much of damage to neither the surrounding areas or marine structures or the nearby birds. So 2 things that we needed to monitor was ground vibration, as I said, and water shock. So you can see in the water, we are going to put hydrophones and measure the water shocks, and ground vibration we are going to put very close to the new berths, so that we can control the vibrations to permissible limits. Normally we lay down the permissible limits based on the type of structure and then the quality of the structure, the foundation, and all those things. That was basically demolition blasting we talked about. Now here I am talking about seabed blasting. You can see this is the rock that I wanted to blast because I wanted to deepen the port. So there, maybe 2 meters, 3 meters, 4 meters. Again, that depends on what charge I can really blast, because I have very closely, associated ships standing in nearby berths, and you can see closely associated structures, like already you can see the surrounding structures very close by, and houses also very close by. So it has to be done in a very meticulous manner. And here is what you are seeing: a splash of water. The detonation has happened, and you can see a plume of water, coming up. So this is just the cycle. It's a very cumbersome operation. Again, the diver plays an important role. In fact, as Professor Rajiv Shekhar was talking about, the use of cyber physical systems can be considered here also, because you can monitor the water pressures, you can monitor the ground vibrations by placing sensors, so that even underwater cameras we can fix, and we can map the fragmentation. Even we can eliminate the use of divers. Basically, it's a very cumbersome operation. Therefore, and on oxygen they have to go down. So therefore, we can allow this not to happen by using cyber physical systems. You can see the charge columns prepared. In fact, these are all custom built actually. And then that initiation, because on surface you can see everything, but in underwater you can't see anything. So you have to prepare a system of laying down the connections. So what you are seeing is a laying down connection mechanism where the 2 rows of holes we are blasting, and you can see at the far end, what you call popping up of water. Basically, it's blasting is taking place here. And again, the monitoring part is a inseparable thing. So you need to monitor, you need to control, because ISM is doing the job and IIT Madras is monitoring this. So there is always checks and balances for such works along with the port. I'll just show you a small video that probably gives us a better idea. So here is the place where I've already drilled and charged, and I'll just take you to the exact blast. Now the initiation has taken place. Now you can see a plume of water coming up, but not much of damage, nothing, and it's only like just lifting up. Now here is a small issue of fly rock. You have an issue of ground vibration. You have an issue of water shock and all. So because the marine structures are very close by and founded sometimes loosely, they're very old. So we need to be very careful in designing these systems. Now let me show you another one. That was a demolition blast, and this is a seabed blast. Here I have drilled, in this area I have drilled 2 rows of holes, deeper by 2 to 3 meters into the rock, as I mentioned. And now I am conducting blast. You can see now splinters is the initiation, and now there's the blast actually that has taken place in the seabed. So you can see the water shock, you can feel the color change, and also, in fact, all these changes can be grabbed through high-speed videos as well as using cyber physical systems, and that will help us actually to have more data and then analyze and engineer the system in a better manner. So this is a new assignment that we have taken up very recently. It's an ongoing industrial R&D project. You can see a naval base very close by, and you can see this is the blast. Again, a ½ kilometer berth we are going to blast off, and you can see the LPG or gas pipelines are very close, at a distance of 15-16 meters. So this is the ½ kilometer long old berth that we are going to dismantle. So this is exercise. Recently we have submitted our methodology and it has been approved by Visakhapatnam Port. Now we are going to work on. This is the actual drilling and blasting charge designs and all. So I think that's the first dimension I wanted to cover. The second dimension is tunneling. As you can see, tunneling is one area where mining engineers are the most wanted choice, I should say. Rather, they can find a greater solace because of the kind of conditions we have in tunnels and the kind of comforts we have in tunnels compared to mines. I'm not saying they should not join mining, but then we have to find out some alternatives or avenues for that. You see, India after China is the next growing market of tunneling, and we have kilometers of tunneling being done already. Many kilometers, thousands of kilometers completed, and a lot of opportunities here. And drill and blast method and road headers and TBMs are one of the major technologies that we teach the students and research out. And those are the things that we can bring into readily and offer. In fact, these are not covered anywhere in any other courses other than in mining. So taking mining technology into underground space, if you see, probably there is no area untouched actually where we cannot apply mining technology. If you see, probably starting from metros, rapid mass transport system creation, to even nuclear waste disposal, to even multi-stored parking, probably all are much safer. Underground space is considered most safer, most environment friendly, saves green cover, probably the most environment friendly. Therefore, if you can take care of the cost factors by choosing a proper technology, commensurating with the rock strength and other important practices as mentioned already, probably we'll be able to achieve. In fact, we have a lot of advances in tunneling technology today. You can see the multi-boom electro-hydraulic drill jumbos of Atlas Copco or many of such companies. Mechanized charging, earlier we used to do all this in manually. As Professor Rajiv Shekhar told initially that we were doing everything, drilling by manually, loading by manually. Now everything has been converted into ultra-scale modernization. You can see the booms operating, drilling the face, drilling the roof, everything. And you can see the face is supported till the roof, the roof is supported till the face. So making the workplace much safer. As Professor Bhattacharya was talking about, vision zero harm is the the vision that we are looking for. And rock bolting is one area where we can we need to do in this, and then the loading and transportation, and then ventilation. In fact, these are the main value chain expertise that the mining technologies have. So we can readily apply this. So I'll not go into details of these operations. One of the technologies that we are now trying to develop, probably where cyber physical systems also can be engaged into. In fact, this is based on that one. You can see the change in color of rock is being detected by the drilling machine while it is drilling. So in fact, this information gets into the logging of the machine, and then this is supplied to the blaster, and the blaster basically loads explosive based on the condition of the rock. If it is soft, it doesn't put any explosive there. So I think this is the expertise that we have at IITACB, and we are offering solutions for rock mass characterization, full optimization, control blasting for damage control of the tunnels, because we don't want to unnecessarily overbreak the tunnel. So in a recent study that we have done, particularly with our applied geophysics department, we could map actually the pre and post blast damage that can be caused while blasting. You can see the drill holes are here in the vertical ones, and around that, after blasting, you can see the blue zones are increasing. The increasing blue zones means the velocities are reducing. That means rock mass is becoming weaker and weaker. So if it is for blasting, obviously we can see whether it is blast-induced damage or whether it is stress-induced damage or structure-induced damage. All those things can be detected by seismic imaging. So this we are applying in tunneling, and this also helps actually to design our blasting system also using electronic detonators. So I think I'll not go into details. I'll skip this. This is the strength that we have. How do we characterize? And these are the technologies. And a recent study for an L&T sponsored tunneling case for a defense project, you can see we could establish based on the quality of the rock mass what pull actually I should go for. Pull is basically the advance I can make in one round of blast. So it is dependent on the quality of rock mass. If I have a good quality rock mass, I can go for longer pulls. But at the same time, then I need to control the overbreak also. The longer pulls also invite overbreak. So how do I control overbreak? So it's a two-stage, variable problem that we need to answer. So we could answer, and we gave a solution to them and design to them. Ventilation is another area that mining engineers are every day doing. So obviously this can be straight away transferred to tunnels and caverns. I think I'll not go into details of this road heading technology and tunnel boring machine technology. We have specialized tests in the institute that we can do, and I'll not go into details of these. And then, as I said, tunnels also, one of the areas that one of our colleagues have recently completed is the damage of basically mechanical, hydrothermomechanical loading that normally is caused in nuclear waste disposal sites. In fact, he has completed one R&D project and came up with a design of how do we dispose these nuclear waste canisters, how do we space them, how do we put them, in what kind of, quantity of bentonite and all. So you can see it is nothing but a nuclear, if you see the architecture of a nuclear waste disposal site, particularly in underground, because this is considered the safest compared to any other disposal, it is just like hard rock mining. So designing this would be, the most appropriate way, and with modeling initially, and then storing in tunnels, which are safely, safeguarded for all kinds of deformations, and it can be in shafts, and you can have an underground research laboratory also to do research on the various aspects of permeability, porosity, the heat, the thermal loading, everything. And lastly, the caverns, third dimension, which I wanted to cover. Caverns house many facilities today. If you see, multitude of uses are there. The power houses today, hydel power particularly, houses all the powerhouses in underground caverns. Oil storage is another area where we are contributing. Strategic bases, and you can name, there are a number of facilities. I think I'll not go into details. It's a very big, project. Hydel project is a very big project involving a lot of tunneling, a lot of cavern excavation. And then you can see the support design, which is again a very important facet of mining, so which we can straight away transfer. Only thing is it has to be much more safer, because the duration of this opening would be more than 100 years. LPG also, again, the thermal capacity and storage, you can see that. So I think due to time constraint, I'll not go into details. I think these are the important studies that we are doing: the permeability, stress-induced confinement, self-standing capacity, and thermal capacity studies, so that we can design the excavations in a more holistic way. In fact, IITACB is engaged since long to create these facilities by designing some specialized tests and designing for blast, control of overbreaks, and we can see the application of mechanization, and even including metros also. I think the presentation gives you the details like which are the major strength areas of mining technology, which can be directly transported to other areas. And of course, these are some of the facilities. I think ports, tunnels, and caverns are lifelines unquestionably. Most of the studies are interdisciplinary and call for advanced modeling, design, instrumentation, operational analysis skills. And advanced rock mass characterization, right material system selection, optimization, must go hand in hand to reap the benefits. And I think the use of automation, IT/OT integration, data analytics, and cyber physical systems are the need of the hour to get into these areas. And now the question is, academia industry engagement is the key, and we are there, but then we are still we have to move ahead. Thank you. Thank you for your attention.
Thank you so much, sir. I wish we had more time so that we could have heard more from you and had some more time to ask questions also. But unfortunately, we have run out of time. I just can perhaps ask one question each to Professor Bhattacharjee and Professor Murthy. So one question that often kept repeating in the chat, question and answer chat for Professor Bhattacharjee is that how optimistic are you about underground coal mining? Now that we are seeing that there is a declining trend, and of course, costs are also quite high in comparison to open cast mines.
Right. My answer is that if you talk about cost first, because open cast mine believed to be less costly, but my experience is that if you consider the cost of environment, you add up to that cost of production with in open cast, the cost will be very, very high. And my experience personally in Australian mines is that at some point of time, 2009-10, the cost of underground production was $45 a ton, whereas the cost of open cast production was $100 a ton. So there is no question about that. If we are compromising with other things, the cost may come down, but now I think that is not possible. So we'll have to go. Now, next question is how we are optimistic about underground mining. We are going deeper and deeper. Perhaps open cast may not be the solution. We have to go. There's no way out but to go for underground mines for deeper deposits. So I'm sure that the things will change now.
Sure. Thank you so much. So that was very short and brief and sweet answer. I also would like to support that idea because, in fact, in open cast mining, even the social cost, for example, of displacement of large number of people is often ignored. So I support your idea, Sid, that it is time for us to go more and more underground. The question that I have for Professor Murthy is one particular question from one of the companies, perhaps whom you have worked with, I guess, is that how do private sector companies submit proposals and work with you?
We are working already. We are working with L&T. We have already recently taken up, and we are working with IITACB. In fact, the projects which we talked about are all private companies only. So we have different modes of engagement. Industrial R&D we can do, consulting we can do. We can also do testing, whatever is required. But then not on a routine basis, but then on a specialized assignment we'll take up.
Okay, great. Thank you so much, sir. And it's been great at least seeing all of you, my old professors, and interacting with the director ISM. Thank you so much for your time. Over to Dr. Sushila now.
Thank you very much, Dipesh. And thank you for this very interesting session today. So just a quick wrap up. India's power demand is going to grow by 80% in 10 years. And while coal as a percentage of the energy basket will reduce, in absolute terms, it is going to still be an increased number. And therefore, as Professor Shekhar said, coal ain't going anywhere. So in that context, we looked a lot at various technologies, what is happening with mining. We also looked at the fact that apart from looking at renewables in terms of their emission and the rest of those kinds of issues, we also have to look at the materials themselves and what happens to them. So consider these energy sources, the mix of these energy sources more holistically rather than looking at them in isolation. We do have the coal resources that are needed, but and then again, but there are a number of challenges because of practices that have grown over a period of time. And we saw a number of strategies for how to move gradually from open cast to more and more of underground. Other economics-based action plans such as closing uneconomic mines and amalgamation and so on, as well as important issues that were flagged like energy audits and energy benchmarks and defining what those really are. We saw many actions that were identified in the course of this webinar today, including things like repurposing reclaimed mines so that they are put to some reasonable kind of use. But the other, obviously the most interesting part of this discussion also went into looking at mining 4.0 and what it really means. Starting with putting sensors everywhere, looking at satellite and drone data, for example, that add to everything else, all the other data that is flowing in, which obviously means tons and tons of data that is being generated in real time because mines are not static, and we need to look at these dynamic data build up. And obviously you need strong AI and machine learning kind of systems to sit on top of all of that to create those dashboards that would make it actionable for everybody, including policymakers. So we had a reasonably detailed understanding of what cyber-physical systems are for mining, and that was very interesting too. It's also very heartening to know that the SAGES machine developed at the IIT Dhanbad, what it does in terms of improving safety and efficiency and so on. And so it was really about the importance of autonomous mining and automation in mining. But finally, the technologies that are used in mining have an application way beyond just mining. And we looked at seabed and what the application of those technologies in other areas that are not to do with mining. And we also saw that seabed and asteroid are probably the new sources of mineral that need to be mined at some point of time. And what is the outlook with respect to those? Finally, the importance of industry-academia interaction to make sure that we address these issues in a timely manner and also make them meaningful for India. And I just want to mention here that the IIT Alumni Center, Bengaluru, does exactly that. We help bring together industry and the IIT system, as well as the alumni network. We help to bring all this together to be able to solve large challenges that the country faces. So, happy to be involved in anything that would help. With that, I just want to thank Professor Rajiv Shekhar, Professor R.M. Bhattacharjee, and Professor VMSR Murthy for their wonderful presentations. I honestly wish we had put aside more time for these presentations. We hope that we can do something more detailed in the future. And Deepesh, thank you very much for having moderated this session very well. For our audience, apologies that we could not take all of your questions. We hope that, but we do have your questions and we will pass them on to the speakers, and let's see if we are able to get answers to those. That would be wonderful. So with that, thank you very much again, and good night.